Hi, now we are going to move to the next section about moment and moment generating function. First, let us start with moment. Okay, moment is defined to be as mentioned here, the moment of random variable or of a distribution are the expectations of the power of the random variable, which has the given distribution. If x is a random variable, the R moment of x is as defined to be as indicated here, which is also can be mentioned as mu mean, okay, expected of x power of R. Therefore, the R moment about the origin of the random variable is the expected value of x power R. Okay, so this is the standard definition for moment. So the moment of R is just an expectation of the x power of R. Okay, so the first moment will be the expected of x, okay, which is equal to mean. Okay, and then you can have expected of the second moment, third moment, and so on. So it will be always the expected of the x power of R. And then next one is the central moment. The R moment about the mean of a random variable x is the expected value of x in this term deviate from mean power R. Okay, so we can write the formula as the central moment of the R is the mu R as the expected of x deviate or minus mu power of R. Okay, so this will be the discrete random variable formula, and this one will be the continuous random variable. Okay, so as you can see, it is always as this term power of R multiplied with the function fx. So fx in this case is a PDF, but fx in this case is a BMF, because this one is a discrete case, this is the continuous case. Then the R moment about the mean of a random variable x is sometimes called the R central moment of x. Okay, so as here mentioned, so we can define our mu1, mu2, and so on. So we define as mu1 as the first moment, okay, and then mu2 is the second moment. Okay, so from here we can say that the R central moment of x, okay, can be written in this form. Okay, and then variance can be also written in the moment form, which is the second moment, or ex square, minus the first moment power 2, okay, or minus ex and then square the term. Okay, so this is just a different format of writing, yeah, but the formula is always the same. Okay. And then next we move to moment generating function and its property. Okay, first of all, we would like to know what is meant by moment generating function. So as a definition, it gives us the following formula. So it is written as expected of the exponential power of tx. Okay, so if x is a discrete random variable, it will be the sum of the exponential power tx multiplied with the BMF. If x is a continuous random variable, then the moment generating function is obtained as the integral of the exponential power tx multiplied with the PDF fx. Okay, so how to form this kind of formula? So we can move to the other file to show how we can obtain such kind of formula. And then after knowing how the idea behind, we can further study the property and how we can benefit using moment generating function. Okay, so to do so, we move to another file. Okay, so this is the standard formula as mentioned in the file just now I show you. Okay, then here we are showing how to get to this kind of formula. Okay, so we take the example of okay, discrete case. Okay, so how to get this formula. Okay, actually to prove the moment generating function, we have to apply the so-called Maclaurin series. So the Maclaurin series is taking the following form. So it is an expansion of the function ft as a sum of the function derivative power of n, okay, given the n with the value 0 divided by n factorial multiply with t power n. Okay, so if you expand this formula, it is looking in this way. Okay, so it can be written in this expansion. Take the following series. So this is called the Maclaurin series. Now we want to apply the Maclaurin series to show how we can obtain the moment generating function formula. Okay, to do so, because here we don't know what is ft look like. So as an example, we replace the ft our function as exponential function power tx. Okay, so we want to replace the formula inside here. So this is without derivative. This one is the first derivative f1, second derivative, third derivative, and so on. Okay, so we apply this. Actually this one is equal as the derivative of the function. Now we replace the ft function with this term. Okay, and then the first derivative of the function as here give us x, and then second derivative third until z, okay, will give us, if we solve it, the derivative first, second, third, and so on will give us x squared x power 3 until x power z. Okay, so if we replace here, will be like that with the power. So yeah, our ft is etx. Okay, so applying the Maclaurin series. Okay, this is our Maclaurin series. Exactly, we apply, putting the ft here, replace with e power tx, and then solving as just now we solve already x squared x3. So which is replace the term here. Okay, the term, this term with x, and then x squared x3 and so on. Okay, as you can see here, we replace the f1, f2, f3 as we obtain from here with x, x2, x3, and so on, and then multiply with t power 1, t power 2, and so on. That's why you get this, exactly follow the Maclaurin series, okay, to solve the function e power tx. Okay, so this is what we get using the Maclaurin series to solve e power of dx. And then next, so this is e dx. We can expand into the Maclaurin series like this. Now we want to find the expectation of this term. Okay, because MGS is defined to be the expectation of this function e power dx. So we want to find the expected of this function. Okay, so expected of this function as defined by MGS should be the sum of this term multiplied with the function fx. Okay, so the sum of the tx e power tx. Okay, this one we already solved using the Maclaurin series above. We just replace or substitute here. Okay, so we solve already using Maclaurin series, and we solve our solution of for e power tx. E power tx here we replace here times fx. Okay, and then we expand it. So okay, so we just expand it 1 times fx, and then this term times fx, this term, expand it. So we are getting this long series, and then okay, sum of fx will be equal to 1. This one we already learned, right? As a random variable, the one of the property should be sum of x, sum up will be equal to 1, and then the term x times fx, actually this one we learned before, this one will be equal to ex, right? Our expected value, ex is equal to mu, so t times mu, or expected value, and then okay, so this is our expected value, and then the third term is this term multiply with this one. So this one we learned already, our moment. This one will be the ex square, right? The second moment. Okay, so this will be our second moment, and then this one will be our third moment, multiply with this term until our term. Okay, so in the expansion, the coefficient of this is mu power r, the r moment about the origin of the random variable x. Okay, so actually this is our moment generating function formula. Okay, so the formula is will give us if we are written in the moment form, it is equal to 1 plus the first moment multiply t, second moment multiply with this term, third moment, fourth moment, and so on so forth. Okay, so we can utilize this, the meaning of the moment generating function. If the question asks us, is the question give us moment generating, and they ask us to find the first moment, second moment, third moment, so we might be able to find the moment. Okay, so we already know this is the first, the second, the third, it taking into this sequence. Okay, so by so we move back to our formula here. Okay, the property of moment generating function. Okay, so the property here, okay, well, actually this is a standard formula of MGF. So the property here say that if the moment generating function exists, then for any positive integer k, this is k time of derivative. Okay, if we take the k time derivative by setting the value equal to 0 here, the value of x here, then it will give us to the number our k moment that we would like to find. Okay, so okay, example here. So this is the standard formula. If we take our moment generating function derivative, okay, so we will be able to find the number of moment that we want to find. Okay, example, we want to find the first moment, then we just need to do the first derivative by setting the value of t equal to 0. Then it will give us the first moment. First moment is expected x, or mean. And then to find ex square, okay, we need to do the second moment, okay, and then set the value of t equal to 0. So we have to do power dot dot second moment, okay, then it gives us the second moment. And third moment, you have to do the third derivative by setting the t equal to 0, okay, and so forth. So the same apply to the continuous case. Okay, so this is the discrete case and continuous case as well. Okay, then third property is it say that if you have two random variable x and y, so you want to find the moment generating combination of the moment generating for x plus y. So you can obtain using this formula. H is a multiplication of the moment generating function of x with the moment generating function of y. And then number 4, okay, so this is the moment generating function for a term, okay, x plus a. A is a constant. So to find the moment generating function of x plus a, okay, it will give us the e power of at times the moment generating function of x. And for the term of bx, the moment generating function of bx will give us the moment generating of bracket b times t. And then for this term, it will give us the e power of this term multiplied with the moment generating function of x power t over b. Okay, so maybe we can move to the example to see, okay, or further question. Okay, so for we are given a fx function here, and we need to find the moment generating function, okay, for this, okay, function. Okay, so we might need to apply the formula listed here. Okay, so this is the continuous case. We need to have an integral of e power tx multiplied with fx. Okay, so we move back. So we have to use the e power of tx because this is s, so x multiply with fx function here. So we just take out the term half here, and then this term is here. Okay, so we solve it. Okay, this we have to do the multiplication, simplify to this term. After that, we solve the integral function. Okay, which give us like this. Okay, and then finally we are able to solve it. Okay, and then another example. Okay, so exponential distribution with parameter lambda. Okay, so using the moment generating function. Okay, so this is a standard formula for MGF. Okay, so if your fx take the exponential function, so exponential function, so this is the exponential function, so in the other chapter we will learn what is mean by different type of random variable. One of it is exponential function, so it is a standard distribution function. The function of PDF for exponential is this. Okay, then we multiply following the formula of MGF. We have a multiplication of this term and integral, and then we solve it, we get this. Okay, so we note from this the derivation that for the exponential distribution, the moment generating function is defined only for value of t less than lambda. It should be less than lambda, right? T should be less than lambda, otherwise this becomes 0, is something cannot solve, right? No solution. So differentiation with the moment generating function will give us the okay, the moment term. Okay, so this is, okay, the first derivative, the second derivative with respect to MGF will give us value like this. And then as mentioned here, we say that if we want to find the mean, we have to do the first derivative of MGF and then set the value 0. Okay, so then this is, we set the t equal to 0. Okay, so when we replace t with 0, we will get this. So this will be our first moment, or ex. And then same to solve for ex squared, the second moment. We do the second derivative. So this one we already have empty, we need to do the second derivative. So you will get this as your second derivative. And then setting t equal to 0. Okay, we replace 0 here. We will get this as our solution. Okay, so this one will be our second moment. Okay, then to find the variance, so the variance is as defined here. We just substitute what we find here and we get the solution for the variance. The next one, if x and y are independent binomial random variable with parameter np and mp respectively, what is the distribution of x plus y? Okay, so we would like to know. Okay, so the question gives us both x and y following the binomial distribution function, and x is distributed with parameter np, y is with mp. Okay, then we want to find how about the x plus y distribution. Okay, so we can utilize the moment generating function, this formula, as we learn here in number 4 here. Number 3 here, x plus y. So we apply this formula, and then we are able to solve it. Okay, so of course, first of all, we need to solve for mtx, mty. So this one we will learn in the other chapter, the moment generating function. So it will take this form, and then we just replace with the term with the mean with p, and here the size with n, and then for y, so this is for x, this is for y, is replaced with m, but the parameter with p the same. Okay, and then we solve these two terms, we will get this. Okay, so that we say that yeah, x and y are binomial distributed with the parameter m plus n and then p. Okay, so if you are not very sure about this binomial distribution, I will teach you in the other chapter. You will be clearer. Okay, but the idea